In this video, I want to talk about Pascal's triangle. Now, Pascal's triangle, I am introducing at a point in my video series. I haven't talked about any kind of counting principles or combinations or permutations or factorial. So to start this video, I'm going to start with that. I can hope to do another video in the future going over fundamental counting principles in general and just talk about how those are used. But for now, to understand what a factorial is when we have n with a little exclamation point, okay? So what this means is I'm going to take n, and then I'm going to multiply it by 1 less than that number. And I'm going to repeat that into 1 less than that number, or 2 less than the overall number. And what I'm going to do that is repeat this until I get to 2 and 1. So it's a repeated multiplication of all the numbers up from 1 up till that number. So I've got an example here. 5 factorial would just be 5 times 4 times 3 times 2 times 1, which would be equal to 120 when you multiply it all out. Okay. The reason why this is important to understanding is this leads us to the combinations formula. Now, this video is meant to set up a video on binomial expansion, and the understanding combinations and Pascal's triangle is very important to that video. So this is its predecessor, okay? So the formula of, let's go over the idea of what a combination is. A combination is a selecting of objects from a group in which case, in which I don't have to worry about the order in which I pick them. So for example, I've listed out A, B, and C. Let's call these my objects, okay? So I have 3 objects, okay, in this group. And 3 is always a nice one to do because it's small enough that you can get all the examples out of the way, okay? Let's say I have 3 objects and I want to choose 0, okay? I don't want to choose any objects from this group. How many ways can I do that? Well, there is one way to do that, and that's by not choosing any of them. It leads to the idea, if I have 3 objects and I want to choose 0, the default might be to say, oh, there's 0 ways to do that, because that's ridiculous. Why would you do that? But the act of not choosing is still a choice, okay? So let's go through systematically. What if I want to choose 1? Well, and I'll go back to choose 0 for a second. This is usually in set notation is listed as a 0 with a line through it. This is called the empty set. The empty set is a set. What if I want to choose 1? Well, let's list out the possible ways to do that. I could choose A. That's one way. I could choose one of the 3 objects. I could choose B. That's another way of choosing one object. So I'm choosing A or B, but I'm not choosing both, in which case the last option would just be to choose C. So there are a total of 3 ways. And I've listed them all out. The only way to choose one is to select one of the 3 objects. And there are 3 objects, there are 3 ways. Okay, so let's talk about choose 2. And now I'm using the word choose. Choose is the word that's often associated with combinations. I'm choosing them, okay? So these words kind of go hand in hand. So I've got a list of A, B, and C, my objects, and I want to choose 2 of them. Well, in this same mindset, I could choose A and B. So now I can choose 2 at the same time. Or I could choose A and C. Those are all the possibilities if I chose A. What if I didn't choose A? Well, then I have another one in B and C. Okay? Are there any other ways? Remember, order doesn't matter in this case. So if I choose A first and then B second, that would be the same as choosing B first and A second. Order doesn't matter. So these are the only 3 ways. If you were to say that order did matter, then you'd be talking about permutations, in which case we'd want to go through BA, CA, CB, and so forth and so on, okay? Finally, how many ways are there to choose 3? This means I'm choosing all of the objects. Well, it's a similar mentality to choosing 0. If I want to choose all the objects, then I just choose all the objects. The only possible way to do that is to take A, B, and C. And so that's one way. Okay? So that's the idea of combinations. But there's got to be a formula, right? Say I had 100 objects and I wanted to go through all their different possibilities. I'm not going to have to list off 100 different objects and then, okay, this and then this, or A and B, or maybe A and Z. No, that's where the formula does come in. So the formula involves factorials. This is why it's important to understand the idea of factorials. So n factorial divided by r factorial times the quantity n minus r factorial. And so the n is the total number of objects. So in my example, there would have been 3. N would have been 3. And then r is the number I'm choosing. So r would have been 0, 1, 2, 3, depending on what a specific question would ask. Okay. Really quickly, I want to discuss some identities from this. Okay. Notice that it doesn't matter how many objects I have. So this idea of n choose 0 is the first identity list. It doesn't matter how many objects I could have 100 objects. If I want to choose 0 of them, using the same mentality as my ABC example, there's only one way to do that. So no matter how many objects you have, if you want to choose 0, that's 1. Likewise, we can use the same mentality. If I have 100 different objects and I only wanted to choose one of them, well, if I list out all those possibilities, that would just be each object listed individually. So n choose 1 is always going to be n. I'll go to the fourth one really quickly. N choose n, that would be how many objects, say 100. How many ways are there from 100 objects to choose 100 of them? And that's always 1. If you're choosing all of your objects, you can only do that by choosing all of your objects. That is the only way that can happen. Now, this last one that I'm going over is n choose n minus 1. Okay, well, let's look at that from the perspective of our example. 3 objects choose 2. So n minus 1 just means 1 less than the total object. So if I had 100 examples, then I might choose 99. That's what this notation stands for. And this identity also equals n. And I go over these identities because this is going to set up Pascal's triangle quite nicely. Pascal's triangle will be a way to use combinations without having to go through this formula. Now, I think personally, n choose 0, n choose 1, and n choose n, those identities are kind of obvious. If you understand the process of what's going on with combinations, then you understand why these identities are true automatically. If you don't understand, leave a like and a comment, and I can make a future video on more combination stuff. However, I want to go over this last one, or rather the third one listed. I want to prove that. So I'm going to get into my first ever proof on my channel. Let's go ahead and prove that n choose n minus 1 equals n. Well, I'm going to set up n choose n minus 1. And proofs were always easy for me when there was a formula involved. So remember, again, the formula of n choose r is n factorial over r factorial times n minus r factorial. Okay. So using these numbers, n is just n factorial, so that's the same. But notice r in this case is n minus 1. So instead of r factorial here, I'm going to write n minus 1 factorial here. And then n minus r, again, r is n minus 1, so I'm going to write it as n minus, because it's a minus, I'm going to open up another parentheses, n minus 1, pardon me, make that a little bit neater, n minus 1 factorial. There we go. So this is just setting up the formula. In proofs, if you have a formula you can use, by all means use it, but you have to use it in generic form. Okay. Now, this looks like just a bunch of mathematical notation right now. How do we simplify this down? Because that's going to be the goal, is to simplify it down to a point where I just have n at the end. There's a really neat trick in factorials. Take our example 5 factorial. We listed that off as 5 times 4 times 3 times 2 times 1. That's what a factorial is. Notice something, though. This 4 times 3 times 2 times 1 is just 4 factorial. So if I wanted to, I could rewrite this as 5 times 4 factorial. And this is a technique that is common. And you could do this as many. You could say 5 times 4 times 3 factorial and do that as many times as you need. However, I'm only going to need to do it once. So I'm going to write this numerator as n times n minus 1 factorial. I'm also going to distribute this negative here so I can do all my simplification at once. And notice I get an n minus an n, so that will cancel out. And the negative times a negative gives me a positive. So when I rewrite my denominator, it's going to be n minus 1 factorial times 1 factorial. And now what this creates is a cancellation. Now, when we're talking about the basic idea of a factorial, we can only cancel this if it does not equal 0. So will a factorial ever equal 0? And that's no. So we can do this cancellation, no problem. And 1 factorial, well, 1 times all the numbers up to 1, that's just 1. Okay, and I should say integers. I should have been saying integers this whole time. So I have 1 in the denominator. All I'm left with in the end is just n. So the reason why I take time to prove this is those other identities, the n choose 0 equals 1. You could prove that doing the same thing we just did. Same for n choose 1 and n choose n. But to me, using the mentality of combinations, they're kind of obvious. The n choose n minus 1 identity is not obvious. Okay, that's why I wanted to go over the proof to demonstrate that this is indeed true. So that leads us to the main event of this video, Pascal's triangle. And I've already got it started here with 3 1s positioned in a triangular fashion. Okay, so the first thing we need to start is by understanding that this very first one is the 0th row. Okay, that doesn't really make any sense. What do I mean by 0? That's just kind of my way of referencing it. The 0th row means this is 0, choose 0. So if I have 0 objects, how many ways are there to choose 0 of them? Well, it seems kind of intuitive. I don't have any objects, so I can't choose any to begin with, so there's one way. Okay, let's run that through our formula, though, really quickly. So 0, choose 0. I don't need to rewrite it. It's right there. Equals 0 factorial over 0 factorial times 0 minus 0 factorial. Now, this may seem like it's problematic because 0 minus 0 is 0, so I get 0 factorial over 0 factorial times 0 factorial. So what do I have effectively 0 over 0? And the answer is no. And that is that because 0 factorial is defined to be 1. I'm not going to go over the why in that. I'm going to offer you a little incentive to discover that for yourself. If you would like to see it in a future video, leave a comment in the comment section. Okay? But 0 factorial is equal to 1, which means I have 1 over 1 times 1, which gives me 1. Okay, great. So this is the first official row of Pascal's triangle. The only reason why I put this top one here is because it makes it look like a triangle. I feel like with the absence, it's like a triangle with its tip cut off. Okay? This first entry right here is 1, choose 0, and this other one is 1, choose 1. Of course, anything choose 0 is 1, and anything choose itself is 1, so that makes sense. Now, that leads us to the basic structure of Pascal's triangle. If anything choose 0 is 1, that's what's going to appear on this outer edge. So we're just going to get a bunch of 1s going down the sides here. Okay? Likewise, if anything choose itself as 1, then we're just going to get 1s. Let me make sure I get the same amount going down this side. But this also leads us to an additional property. If I have n objects, there are always n plus 1 different ways to choose objects from them. So what I mean by that is when there are 0 objects, there's one possible combination I can write out, and that's 0, choose 0. When there was 1 possible objects, it was 1, choose 0, or 1, choose 1. So that was a total of 2. Okay? So 2, choose something. Well, let's think through it. That's choose 0, choose 1. I'll write it out, actually. 2, choose 0, 2, choose 1, or 2, choose 2. So in the second row, I should have 3 entries. Well, anything, we know this is 1, we know this is 1, and 2, choose 1 is, or anything choose 1 is itself, so that should be 2. So in this middle entry right here, and I've left a lot of space, but this is how we know that the row is done. So when I go to the third row, I should have 4 numbers in this row. Well, let's list them out. Actually, we did them in the previous problem. I'm not going to list them out. That was 1, 3, 3, and 1. Now we're getting a little unfamiliar territory. Do we have to go through the calculations of the combinations formula to get 4, 5, 6, and so forth and so on? Because it's plain to see this triangle can extend to infinity. We can extend this for as far as we need. Generally, we don't need more than the first 4, 5, 6, or maybe 7 rows. But, okay. Well, notice this pattern. We get 1s on the outside. That's a good way of setting it up. How do we get the middle entries? Is there a nice little simplistic way we can do it? And the answer is yes. Notice that we've got 2 here. 2 can be written as 1 plus 1. So I add the 2 previous terms together to get it in between. Notice that 3 is 1 plus 2. Same thing over here. 2 plus 1 is 3. So if I'm adding 3 and 1, I get 4 here. 3 plus 3 is 6, and 3 plus 1 is 4. Let's go ahead and check that. This entry right here would be 4, choose 1. That's 4. That makes sense. This would be 4, choose 1 less than itself, which is 3. That would also be 4. 4, choose 2. I'm just going to prove that with the formula, and we're going to constitute this as a informal proof that I am right, and you can take my word on it. So 4, choose 2 is 4 factorial. My r is 2, so 2 factorial times the quantity 4 minus 2 factorial. Well, 4 factorial is 4 times 3 times 2 times 1. Okay, so that's 4 times 3 is 12 times 2 is 24. And there are ways to simplify this, but I'm just going to go straight calculations. 2 factorial is just 2 times 1, so that's 2. And then we get 4 minus 2, which is 2. 2 factorial we just discussed is 2. Let's simplify our denominator, so that'd be 4, and we get 6. All right, so we're going to use this rule moving forward, because it is true. 1 plus 4 is 5. We get 6 and 4 is 10. Another 6 and 4 is 10. And 4 and 1 is 5. Notice there's also a symmetry here. And there's going to be a symmetry in every row. If you are in an odd number row, like 1, 3, 5, 7, so forth and so on, you're going to have the same terms building up, and then once you get halfway through that row, you just repeat the number you had previously and then repeat the pattern going back the other way. So for example, 1, 5, 10, I should have 6 objects. That's 3 done so far. And then going the other way, I'd go 10, 5, 1. So that's if you're an odd number row. If you're in an even number row, you're going to have a build up to the number in the middle, but you're not going to repeat that number. You're just going to work your way back down. Okay, so last row, we get 6, 15, 20, 15, 6, and then 1. And notice, again, we can extend this pattern forever as we need to. If you like this video, go ahead and leave a like and subscribe. If you'd like to see future videos, please leave a comment in the comment section, and I will see you for the next video. Thanks for watching. That went longer than I expected, but I think I'm okay with that. Binomial expansion.